Are all of these on the computer?
Yes,
Or
they are.
online, I mean?
Yes, they are.
Okay.
Yeah. Okay, so now yesterday, I want to connect this to what we did yesterday. Yesterday we talked about similar triangles, and remember one of the things we said was that what we're doing now is virtually the same as what we did earlier in the year with congruence. Remember we had all our congruence relationships, side, 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 angle, side, angle, angle, side, right? And then now we're doing the same stuff for similarity. So yesterday we introduced the angle-angle similarity relationship. If two angles of one triangle are congruent to two angles of another triangle, if we know that to be true, then they're similar triangles, guaranteed. We're going to add some stuff to that today. We're going to add a couple more similarity relationships. Okay, here's one of them. Side, side, side. Similarity. Now this is different. We had a side, side, side congruence relationship that said if the sides of one triangle are congruent to the sides of another triangle, then the triangles have to be congruent, right? This one is different. Thank you. This one is different. This one says if the corresponding sides of two triangles are proportional, then the triangles are similar. Meaning, well, now you describe that to me in your own words. What does it mean if the corresponding sides are proportional? There.
All the sides have the same proportion to them.
Yeah, okay, all the sides have the same ratio or proportion or fraction, right? So in other words, if we, let's color code these. If we know in these two triangles here, we've got a big and a small version, it's always going to be that way with similar figures. We're going to have one that's bigger than the other, but they're just scaled versions. The angles are all the same, right? They're all congruent. So let's say that side AB, we'll call that the red side. So the big red side has to be proportional to the small red side, right? So the ratio of big to small, AB over PQ, must be the same as the ratio of the other corresponding sides. Okay, so let's call these the blue sides.
Greg McCallum, you need to go to Stu Clem's room, which is room 409. Greg McCallum, you're needed to cover a class in room 409.
Okay, so everybody with me? Almost. Okay. So then, if these are color-coded, so the red sides are corresponding sides, and the blue sides are corresponding sides, and the green sides are corresponding sides, then big red to small red must equal big blue to small blue, right? Must equal big green to small green, right? Okay, so there's our ratio. Now here's the ratio, there's the red ratio, big over small. There's the blue ratio, big over small. See what we're doing?
Yeah.
And there's the green ratio, big over small. That's always how we do it. We're setting up some ratio. It doesn't have to be, it could be small over big, but you just got to be consistent. It doesn't matter. You just have to be consistent between the fractions. That's how we do every problem in Chapter 8, is we set up a ratio equation, you know, that's based on this similarity relationship, big to small equals big to small, or vice versa. And then we solve for whatever unknown or unknowns are in that equation by cross multiplying. Okay. So let's look at an example or two here. So if we've got something like, whoops, no, I don't want that either. Not this. Something like this. Okay. Oh, there's the other one. They're going to give them both to us, then we'll look at examples. So we had side, side, side similarity. We also get side, angle, side similarity. So now look what this one says. If an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides, including these angles, are proportional. So now look what we've got. We've got two congruent angles. So angle X is congruent to angle M. And let's make these, how about we'll do pink and green, how about? Everybody agree those are corresponding sides? Okay, so those are the sides that enclose the angle or form the angle. So if angle X is congruent to angle M, and big pink over small pink equals big green over small green, right? Then those are similar. Okay. Those ratios are the same. Okay, whoops, so now let's look at an example. Okay, so take this example right here. These are really hard to see, aren't they? Let me draw those. That's a 9, that's a 6, and that's a 10. Now nobody say anything, but I want you to just kind of stare at those, and if you need to write something down, that's fine, you may not. I want you to see if you can tell me here which of those triangles, if any, oops, which of those, if any, are, yeah, which of those, if any, are similar? How are we going to do that? Yeah, we're just, okay. So take a second and see if you can tell me which. We've got kind of the medium-sized triangles on the left, the small is in the middle, and the big is on the right, correct? Okay? I'm hearing big and small are similar. Well, let's check and see. Okay, if I try big and small, that means the ratios of blue, big blue over small blue, big red over small red, and big, I don't know what that is, big yellow over small yellow should all be equal. Is that true? We set those up. Is 14 over 8 equal to 6 over 4, for example? It's not, is it? It's not, because this reduces to 3/2 and that reduces to 7/4. They're different. Okay, so already we know that these two are not proportional. Okay, because the sides, the ratios of the side lengths are not equal. Okay, now stop me there if that's not. Raise your hand if that is not. Don't do that. Do this. Give me a 1 to 5 on that. Kind of covertly. 5 means, oh man, I got that 100%. 1 means that did not make sense. Do something else. Okay. 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 How we doing? All right. Okay. All right. All right. So we're mostly there. That's good. But let's look at that a different way. I know that if these, all I know about these two triangles, about these three triangles, but we're ignoring that one for the second, right? All we know about those two triangles are side lengths. We know nothing about the angles, right? So the angles can't help us out here. All we've got to rely on are side lengths. Now we know by the side similarity relationship that the ratios of corresponding sides all have to be the same, right? So I ought to be able to set up a group of fractions here. You know, I ought to be able to set up, if I line this thing up, and it's unfortunately it's not lined up right now. These triangles don't, it's hard to see what matches except for the fact that they're color-coded. If I took this triangle and rotated it around, you could see probably more easily that this is a bigger version maybe of this one, right? But we know, they tell us here that the red sides are meant to go together and the blue sides are meant to go together and the yellow sides are meant to go together. We can also see that because if I look at the small triangle by itself, 4 is the smallest measurement, 8 is the middle measurement, or is the big measurement, and 6 is the middle measurement, right? Same thing over here. Now, if these triangles are going to go together, the corresponding sides have to play the same roles in each triangle. The smallest one, the red is the smallest of both triangles, the yellow is the middle of both triangles, and the blue is the longest side of each triangle, right? So those are the ratios that would have to match. I should be able to line all three of those up then. So I've got 10 over 6, 14 over 8, and 6 over 4. In order for this thing to be, for these two triangles to be similar, all of those relationships would have to match. Because when we blow this thing up, the little one up, to create the big one, then each of those sides is going to grow proportionally. It should grow by the same ratio. And we can see here that that didn't happen. It didn't happen because none of these three fractions are equal to each other. If I made these decimals, they'd all be different decimals. This one is 5/3, this one is 7/4, and this one is 6/4, or 3/2, whatever you want to think of it. So because none of those are the same, we know they're not similar. But if any of them are not the same, even if two of them worked and only one of them didn't, still wouldn't work. They all have to be the same fractions. That fraction is what we call the scale factor. Now let's compare that to a situation where it does work and it might make it easier to see. Let's maybe look at, how about these two, the medium and the small. Let's see what happens there if we compare similar sides and see what the ratios are. So if we go big to big, we've got, or big to small, we've got 12/8. The medium sides, we've got 9/6, and the small ones, we've got 6/4. So those are the three ratios. Everybody see that? I'm just doing the length of the big triangle side to the small triangle side. 12/8, 9/6, 6/4. What do you notice about all three of those fractions? What do they all reduce to? 3/2. Yeah. 12/8, if I divide top and bottom by 4, I get 3/2. 9/6, if I divide top and bottom by 3, I get 3/2. 6 and 4, if I divide top and bottom each by 2, I end up with 3/2. So all three of those fractions have the same values. If I put them in a calculator, they're all going to tell me 1.5. Right? Get the same decimal back. So does that make sense? Okay, that these two are similar then, right? But because those two weren't, this is the oddball. That's the one that's not similar to the others. These two are scale versions. The big one is not. Okay, does that help? Okay. Okay, and then there's the explanation that that they had. They just, if we look at the A, B, C, and D, E, F, we can see that they all reduce to 3/2, like we just showed. So those are similar. But if we turn the page and look at the other two ratios of A, B, C, and G, H, J, that was the big one, right? That those ratios don't work out, do they? They're not the same, so they're not similar. Okay, what about one like this? Use the given lengths to prove that RST, so the big triangle, is similar to triangle PSQ. Now what I want to do with this is I need to write a little bit more, so I'm going to actually just take a picture of this page and we'll put it on a flip chart. Okay, so now I got a hint for you on these kind. There's a way to do these that I think helps out a bunch. Do you see what they're asking for, first of all? We're supposed to show that the little triangle and the big triangle are similar. But can you see those two triangles? It's like the little one is sitting on top of the big one. We've got this little one up here that's PSQ, and then the big one that's RST, right? What's oftentimes helpful to do, I think, is to separate the two. Draw two separate triangles. Take that little guy and draw it separately from the big guy. If we do that, let's see, we end up with something like this. That would be the big one. That was RST. And here's the little one, which wasn't that PS what? Q. Okay, let's plug in some numbers. We know that these numbers are 4 and 5, and I know that that distance is 15. So what does that make the whole length of that big triangle? 20. 5 plus 15, right? So that whole thing becomes 20. What's this whole distance, SR? Okay, 12 plus 4, so 16. So can we show then, our goal is to show that those two triangles are similar. Now how could we do that? What are our options? What are our similarity relationships we can rely on? We've got angle-angle, right? Okay. But angle-angle is not really going to work for us here, is it? Okay. We got side angle side, and we got side side side. Does side 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 work?
No,
No? How come?
because we don't have measurements.
We don't have measurements of the third sides. Now, could we calculate those, maybe using Pythagorean theorem?
Yeah.
We could?
No, we don't know if it's like.
It sounds like a good idea, but what's wrong with that idea? When would Pythagorean theorem apply, and when would it not apply? Right triangles. Only time you can use Pythagorean theorem is for right triangles. Well, are these right triangles? We don't know that they are, right? They might be, but we can't depend on that. We don't see any right angles in here, right? So we're stuck. We can't determine the lengths of those third sides, right? So we can't use side, side, side either. The only option is side, angle, side. Are there any angles that we know up here that are congruent between the two? What do you think? Okay, angle S we could say, right? Angle S is a shared angle. That's a part of both triangles, isn't it? Right? If it's a shared angle, it's got to be congruent. So yeah, we do know one thing. We know they share angle S, so there's one congruent angle. Now, we also know the lengths of the two including sides, don't we? The sides that make the angle. So for side angle side to work then, big to small must equal big to small also. Does it? Let's see. If we color code these, so here's going to be our blue side. Here's going to be the green side. Does it work? Does blue equal green over green? The ratios of those two sides? Yeah, it does, doesn't it? Big blue over small blue, 16 over 4, does equal big green over small green, doesn't it? Right?
Yeah.
Okay. We know that. What do those both reduce to? 4 over 1. Sure. Now there's another way we could do this, by the way. If I set up a ratio like this, if I'm testing to see if these are the same, here's another little trick you can always use. If I cross multiply, I have to get a true statement if the ratios are equal. So if I cross multiply here, I get 5 times 16, which is 80, equals 4 times 20, which is 80. So check. Yeah, those two ratios are equal. Does that make sense? Did everybody see that last trick? I think that's helpful because sometimes it's hard to tell if two fractions are equal, right? You can always cross multiply, and if the answers you get on both sides are not the same, then they weren't equal, right? Okay, so this one works.
Yeah.
Okay, this one works by side angle side. Okay. Okay, last one. Actually, I think we're good.
Okay.
I think we're good.
Going to that.